All right, guys. I have something I want to share. Okay. I have been working on building a BBC file for my XC90 for the engine swap from 3.2 liter normally aspirated to 3.0 liter turbo. I broke the high-speed can. My TCM is looking for information from the ECM that my ECM no longer provides. And I unfortunately did this uh, without the forethought of capturing the data. So in a situation like this, a lot of times this is a critical error. How are you gonna recover from something like this, right? I mean, I could just bend the whole thing, just scrap the car, um, cut my losses. That would probably be the smart thing to do, but I'm not really. Maybe I'm. I don't know. Let's just not go there. Maybe I'm smart. Maybe I'm not so smart. I'm more stubborn than smart. So here we are. Let's do that. So, Um, instead of showing you what I've done with my car and um, boring you to death with those details, I'm going to show you how to take a unknown car. Like we don't even have to acknowledge what kind of vehicle this is. I've done a can capture on it. I know what it is, but it's irrelevant. I'm going to show you how to get meaningful information from somewhere that it did not previously exist. Right now, having said that, I have access to a TopDon Phoenix Pro, and I did a capture with SavvyCan with a splitter cable and a simultaneous capture with the TopDon. Now, if you know anything about scan tools, you know that they don't typically support export to Windows, right? You're generally supposed to view the information on the tablet or the scan tool or whatever, and they don't encourage or support or whatever the export of the information. And up until recently, this what I'm about to show you was not really possible, but because of the incredible speed at which the TopDon does the capture on its PCI, I was able to use the information that I found while I was capturing to do what I'm about to demonstrate. Okay, so I am going to open in SavvyCan this log file. All right, this is a capture from a drive that I did in a vehicle on the high-speed can. Now, this is how this normally starts. You go to frame data analysis, and what I have done in the past is flow view, and you can step through and you can sit here and you can play this until you're blue in the face, trying to figure out what these signals mean. This is not the right way to do it. You're really supposed to take the vehicle and interrogate it while it's sitting in the shop on a lift. Do one signal at a time. You know, like heat the coolant temperature sensor and watch it and see what it does, and then or spin the wheels with the transmission in neutral and see if you can get some information from the ABS sensors or from the brake control module, the ABS module. Try to figure out the information that's being transmitted that way, right? But we don't all have the luxury of doing that. I don't even have the luxury of doing that. So I did a high speed active capture, like driving capture, and in the interest of brevity here, I'm not going to like go through all of this. I'm just going to go right to where I know the information is at because I did look at this before I started to record, but we're going to look at it like you've never seen this before, and I'm assuming that you haven't. So let me go to flow view. Right, I'm sorry. Frame data analysis. Sorry, at 12A is what I'm wanting to look at, right? And you can learn a lot from just like looking at these. See that this is zero here, right? And then all of a sudden it pops up. And then it keeps going until the end of the log. So the fact that it starts at zero right there and then becomes active is a very good indicator that this is going to be something that came on with the key on. And again, I have already looked at this. I already know. This one does the same. This one starts, well, it doesn't start at 0, but it, you know, it becomes active with the key on event right here. And that's something that you could go back and you could look at the flow view and you could try to figure out. But I know that this looks like RPM. This looks like the engine speed signal. So this is the capacitor database editor. Now for, you know, like if you only need one signal or two signals so you can stick it on a gauge, maybe you're writing an app or something like that to put a signal onto, you know, a small ESP32 display or something, you don't have to do all this. But if you're really, if you're trying to reverse engineer the car so you can motor swap it, so you can dash swap it, so that you can turn it into a race car, there are, you're going to need to do this. So this is the node list, the high-speed CAN. I added a message. This is rather, we're going to look at this frame, this ID 12A, and we're going to look at the message that's in the frame, the signals that are in the message. So that, going back to the SavvyCan, right here, these, right here, start at 50 byte bit 56. It actually starts at, so again, I'm skipping over the technical details here, but this is, you'll have to learn about byte order, big endian, little endian, Intel versus Motorola. It actually starts here and goes this way, and if you play it back through the other, through the flow view, you'll watch it. It'll start here, and then it'll come up, and then it'll come back around as it increases. And you can learn a lot about the behavior of a signal from watching it do that, from the progression. Anyway, so I know that these are not RV. And this is a tell as well, because this occurs a lot. So this is idling, probably, most likely. 56 through 60. Let's add it right here. 56. Length is going to be 12. Oh, can't do that. Swap the byte order to Motorola. 12. Call this engine speed. Unit is revolutions per minute. Save this. Go back. SavvyCan. DBC file manager. Put the DBC file in there that we just created. Close this window. Go to graphing window. Add a new graph. High speed CAN, engine speed, copy parameters, add this graph. Rescale the data. Now, boom, look at that. If I did not know this was RPM, or if I want to find signals that are related, that's where this comes in. So I open the log from the TopDon Phoenix Pro, right? I have exported it. I'm going to open it here. These are the channels that were logged. Watch this. Boom. Now, what do we see? Right there. That's this first part of the log right here. You can see the characteristic behavior. I don't think you can see my mouse moving right now. So you just have to, you know, like take a look and see that these are all. I feel like I can actually scale this. To make it look more like the top-down mold. And once we're able to do this, we see that it stops like right here, right? And this is something that I'm needing to work on and haven't gotten to yet. But um, I need to be able to split this fog like, and I have a second capture. So I did this capture. This one was from the ECM, and then, or rather, I'm sorry, this one is from the TCM, and the other one was from the ECM. And you will see that it has the second half of the engine speed. Yeah. Well, the the purpose is not to try to figure this out here right now. Hopefully you can see what I'm talking about. How this is very closely resembles. Oops, where are we at? Probably right here. Oh, this is the part that is kind of tricky, right? There we go. You see, we have this it occurs over here. And once we know that, we can actually go over here and we can look at the air mass, right? We can see what the air mass looks like. And I'm not going to bother you to go and try to find this, but you can you'll be able to actually go and know what the values are because you see I can use my crosshairs here and read what the values are for any given frame that it captured in the top-down log, and then go back in my can capture and correlate the events where my RPM is. I'm sorry, where my air mass, right, is 116 grams per second or 128 grams per second. Then I can see that my engine cooling and things that you wouldn't normally be able to know, right? There's the fuel pressure. You see that whenever the air mass goes up, that the fuel pressure is increasing. So, to me, that should be no real surprise. But, and then you can actually lay the throttle position. Now, this it actually brings a very interesting point, and the last point I'm going to make. And part of what you need to be aware of whenever you're reading from a live log, that there are things called false cognates. This looks incredibly close. These two look incredibly close. The air mass and the throttle position, and they're not really that close, but I can, if I took more time and found a better example, I could show you like the throttle position circuits are nearly identical. And you don't know which one is which. Now, I have created an export as CSV here, and I'm not going to do that right now, but I can get around that. I can get around the false cognate problem by exporting it, going through, correlating the information, and finding the outliers. And that's it. I just wanted to demonstrate this software, demonstrate this proof of concept, and show you that it is in fact possible to get information about a vehicle can without reverse engineering the ECM, without sitting it on a lift and uh, dissecting it. You can literally, with the right tools, with a little bit of ingenuity, go in here and find information that is relevant to your project. And I hope that this helps you. At some point, after I've gotten this a little more cleaned up, where it's a little more performant. It's kind of hacked up right now, like it's okay. It's an okay piece of software, but you see, I don't have a title bar here or anything. I built this little control, and I don't have everything working yet. I have a legend where I can turn it off, but I don't. It said my position does absolutely nothing. I need a little pop up right there, but and you know, um, just a few little things I need to clean up. But anyway, I hope that you enjoyed this. I hope that it wasn't boring. I know it's kind of a nerdy topic, but I hope that it helped you. And if it did, I hope that you will like the content, possibly subscribe to my channel, and leave a comment if you have any questions. Thank you so much. Have a good day.